Welcome. Today we have another event in our CLIMACT seminar series. And thank you for coming, everybody. Just to remind everybody, CLIMACT is the joint center between UNIL and EPFL. And the seminar series is basically one of the pillars of the CLIMACT Center. And so CLIMACT, of course, is like we said, the joint center between UNIL and the EPFL. And the idea is to highlight climate research and teaching and to raise ambition on climate action. That's the ultimate goal of the center. And the Ideas and Action seminars are what you're seeing today. It's every second Monday or so from 12 to 1 p.m. And two speakers are invited to give talks on different topics from EPFL and UNIL and beyond, with a cross-cutting role of raising ambition and going beyond of what's already being done in our research institutes. So just some reminders about logistics and conduct. Please keep your video and microphone off unless if you're speaking. Please be nice. We won't tolerate any harassment. Seminars are recorded and will be posted online, the seminars themselves. And if you want to ask questions, please write them in the chat or raise your hand. And the seminars are bilingual, so please feel free to ask any questions in French or in English, your language of choice, and we will respond accordingly. So just to give a summary of the seminars given already, here's a long list of very exciting topics that were covered already, and you can actually go and see those seminars on YouTube at any time, and we will post the links on the chat. And today we have two speakers. The first one is Julia Steinberger from UNIL, who will give a talk on living well within limits, and then followed up by another talk by yours truly to talk about atmospheric particles and their impacts on health and ecosystems. So with that, I'd like to pass on the baton to Julia.
All right, so it's really great to be able to share a bit about my research on living well within limits. And the way I'm structuring this talk is not just to do advertising for Roger Federer and cars, quite the contrary. No, the idea is really that I wanted to try to see if we can build bridges and if I can motivate some of the people listening to think about this research and to think about whether or not you can participate in this kind of research. So the first point is living well equals what? And the what should be pronounced that way because I come from, like many people, sort of a hard science physics background, and I had no idea what I was doing when I started this. So I'll tell you a bit about what we mean by living well and why it's important. And then I'll tell you a bit what we learn about when we measure empirically the energy associated with living well and what we learn when we model it, and some ideas and actions moving forward. So to get right into it, one of the reasons that researching well-being is daunting is because you're basically picking fights with people who've been dead a very long time, in this case, thousands of years. And that's always, you're always afraid of not coming out looking well. But this is basically the cartoon version, but I think it serves its point, is that going back a very long time, people have been thinking and writing about this in a very sort of intelligent and subtle way. And so when we research this, we also have to be aware of that legacy. So according to Aristotle, he had this idea of well-being being able to live life as fully as possible and flourish within one's society. So it's this idea of flourishing, and it's a very social definition of well-being. Whereas just a few years later, Epicure came on the scene and had a very different idea of well-being, which is probably dominant in the way we understand it today, which is that well-being means achieving the most positive and least negative feelings possible. And I'm assuming that you'll all be able to empathize with this, which is that, like all good academic disputes, the two camps persist to this day. Never let a good academic dispute go to waste. So if you're on team, you have to choose a team. If you're on team Epicure, you see well-being as very individual. Maybe it's related to this concept of happiness or the measure of happiness, including the happiness indicator or the utility function within economics. And if you take utility, for instance, the way it's generally understood is that people signify their utility maximization by spending money in the economy. So in that sense, their view of economic growth is that more income means more consumption, means more positive feelings. And so this is a well-being perspective that's very comfortable with mainstream economics and fits very well with it. So if you're on Team Aristotle, however, you have a very different view of the world. So you see well-being as flourishing. It's a much more social perspective. It's much more closely related to the Human Development Index, which is based on Amartya Sen and capabilities, or the Sustainable Development Goals, which are multidimensional. And the idea, you don't have an idea around economic growth. You probably ever have an idea around some kind of development or some kind of support for human potential as what your economy should be doing. So we write a bunch of things, and we decided that we were part of Team Aristotle. And so if you're interested in this and you don't want to have to go back and read Greek philosophy, I recommend our papers from 2017, where we tried to basically explain this to engineers and climate scientists. And in particular, in this paper, Lyman Steinberger, we explained why theory matters for climate change policy. And we basically spelled it out. So basically how the theory of well-being, and especially its links to consumption, deficiencies in consumption, provisioning context, then leads to different outcomes in climate change application. And just to go through it very fast, basically, if you come from an economic utility perspective, you're going to be wanting your mitigation strategy to be cost optimal mitigation pathways. Whereas if you're starting from a human needs perspective, which is the lower line, you have a very different view of what consumption means with well-being, and your mitigation strategy is going to be much more around equality and consumption reduction. So actually reducing the amount that the wealthiest consume. And so that you end up with very, very different outcomes. The happiness perspective is particularly not helpful in climate research because it basically doesn't have any theory of change that would lead it to endorse mitigation, as far as we could tell. So this is the research framework we used within my Living Well Within Limits project, which is a project that started and is still ongoing mostly at the University of Leeds. I'm trying to bring some of it over to Lausanne. And the main thing is that we have these biophysical inputs, and mainly understood as natural resources as far as we're concerned. In the middle, there's this provisioning system, which is very interesting and we really wanted to study it in an integrated social and physical way. And then social outcomes, need satisfiers from this sort of Aristotle perspective. This is the kind of perspective you have on well-being, and these well-being outcomes that you get once your needs are satisfied. And if you want, we can talk more about that. So based on this framework, one of the things we have to ask is, can we measure how we can do both things at once, which is stay within limits, stay within planetary boundaries, especially with regards to energy use and climate change from our perspective, and also satisfy human needs, so satisfy the social foundation of Kate Raworth's donut. And this, just to give you a flavor of what this research can do, this is a paper by Efim Fogel, which is hopefully going to come out soon because I think it's really great, and goodness knows we've worked on it long enough. So the idea is we're looking empirically at different kinds of need satisfiers and their relation to energy. And what we're doing is we're basically relating them just a normal regression with these two variables, actually a bit transformed. But then we also want to understand what role these provisioning systems, or what we call it the provisioning context, can change that relationship. So we see a relationship between energy and need satisfaction, but how does this social and physical context of the society around change that relationship? And so we have provisioning systems, and then we also have an interaction term between energy and provisioning, and this is doing statistics in a good way, hopefully. And the basic idea of it, just to sort of give you this cartoon view, is that if you just look at the bottom rectangle, the bivariate relationship will look something like this: need satisfaction versus total energy use. But depending on the provisioning context, if you have a high value of a good provisioning context variable, your curve is going to move up, meaning that you need less energy to achieve more need satisfaction. Or if you have a high value of a detrimental provisioning factor, the curve will move down and you need more value, more energy to reach high need satisfaction. And can we measure this? Can we actually see it? So the question is, the answer to that question is yes. And what was really striking is this is sort of an aggregate view of which factors we found to be positive in green and which factors we found to be negative in red. And this is for a large international sample of countries, so representative of the whole world. And we see some very positive factors which have to do with public service quality, electricity access, democratic quality, income equality. So if we have more equality is very beneficial, et cetera. Some negative ones or some insignificant ones like trade penetration, foreign direct investment, we didn't see any effect whatsoever. And two very negative ones, which happen to be extractivism and economic growth. So that's interesting. Anyway, so we can, and we can really see a massive effect of these variables. So I'm not going to go into more detail to it, but I'm happy to share the paper. Another thing we can do is we can model how to get within Kate Raworth's donut, so how to achieve both the living well and the limits part of our work. So this is based on the work of Narasimha Rao of Yale, who's also a co-author and a great colleague on this paper. So the idea was to estimate the energy services required for decent living and their efficient entire life cycle energy footprint. So basically, we come up with some direct and indirect final energy, we start with basic needs that are associated with decent living standards regarding these dimensions of human well-being effectively, and a level that is satisfactory, that is enough for everybody to live well. And then we estimate direct and indirect final energy requirements for them using perfect equality and very advanced technology. So perfect equality, the model is equal for everybody in terms of service access, but differentiates by climate. So if it's a hot climate, a cold climate, it differentiates by demographics, and it differentiates by urban and rural split. So it does have some, equality of needs does not mean equality of energy use when you take all of that into account. And we take into account demographic changes. And so what you can see is that obviously this is a very idealized model, but if you compare it to other models of final energy requirements, for instance, from the International Energy Agency, their reference model keeps growing international energy use. Their 2 degrees model sort of stabilizes it sometime in the middle of this decade, and they're beyond 2 degrees, so lower than 2 degrees, even has a bit of degrowth. The low energy demand model of Arnold Grubler was around 250 exajoules in 2050, and ours goes even well below that, and we're around 160 or 150 exajoules by 2050. And this takes into account population growth. So basic needs can be satisfied for everybody with efficient technologies at 40% of our current consumption. So that's the kind of thing we can do. We can compare it to what that means for current countries now. So you can see that there was a lot of deficiency with respect, so anybody who's below that green line is definitely deficient, but even countries that are above the green line in final energy use in gigajoules per capita would also be in a situation of deficiency currently, because the crucial aspect of our model is this efficient delivery of vital energy services. So then another question we always want to ask ourselves is if it's possible, what are the obstacles that are standing in our way? And here the obstacle is not the poor fake tree trunk, but indeed the car. Just a reminder that Switzerland has the worst car standards. So in terms of CO2 per kilometer, Switzerland is the worst measured of all countries in Europe, as far as we know. And one of the things that we really come down with is that we have growth dependent economic systems that have fossil fuel technologies, and they're really entangled with these industries of fossil fuel technologies at their core. And one way we looked at this was to look at the political economy of car dependency. So we took this is now very qualitative, very political economy, sort of heterodox economics approach, looking at systems of provision, which is a methodology developed by Ben Fine and Kate Bayliss, who was working in our team as well. And what we did is we looked at the entanglement of the car industry, car infrastructure, so roads and parking, land use regulation, that's very car-centric, neglect for public transportation, which in many places is quite active, and car culture. And we ended up basically mapping out this political economy anatomy of lock-in. So basically really showing how these intertwined industries and their dominance in our economies and in our politics really means that we have a hard time getting away from car use. And it sort of tells us what we're up against when we try to transform the system. So just because it's possible to do better doesn't mean we will do better unless we really take this kind of obstacle seriously. So I'm not going to go through this table because it's too long, and you can read the paper if you want to. So ideas and actions moving forward. This is an ideas and actions seminar. So one of the ideas I would take forward is it is possible and interesting to research needs rather than greeds, to put it quite bluntly. And these are some research results I didn't speak about, but Yannick Oswald, through his PhD, has been looking at really mapping out how and why energy use is unequal around the world. And his research has really sort of led us to think about things in a very different way, showing that a more equal world would actually be easier to decarbonize. And so he just published that this piece in The Conversation, sort of summarizing 2 of his papers earlier this month. And I think it's really a new insight that as the world gets more equal, you're shifting energy use towards housing rather than transportation. You're focusing on what people really need to live well, and that's much more around heat and electricity in houses, and much less around transportation. And that therefore makes the world easier to decarbonize. And I think that's an interesting thing. Like, are we researching what people need as opposed to what the economy wants over consumers to consume? And I think that we also need to have a policy focus in terms of guiding policy. I would really advocate for integrating climate and social policy. So focusing on equitable and well-being oriented policies. So this is an example from work that was done with the Wellbeing Alliance. It was led by my colleague Milena Bux at the University of Leeds, but we really came up with mapping out different categories of policies that help with well-being and that help with climate and environmental goals, and this is hopefully positive. And as well, for me, it's become very important to link understanding and action. I do not believe that the urgency of the climate situation allows for gradual transitions, either in research or reality. We kind of have to be a bit more bold and a bit less dependent on knowing exactly what we're doing all the time. And really, we need to transform things quite a bit. From my perspective, my interaction with popular movements, including student strikes, Extinction Rebellion, the Sunrise Movement, is that these movements realize that they're taking the warning very seriously, but our research is not always there to support them. And for me, it's very important that our research is actually supporting the people who get it. These people might not be governments all the time, they might not be policymakers all the time, but there is definitely an audience and an appetite for really transformative research. So I will leave it there and look forward to discussion.
Many of you know me involved in CLIMACT, but maybe some of you don't know much about what my research is about. So today I thought about talking a little bit about aerosol particles and their impacts on ecosystems and health. And I'm going to sort of give also a central importance on how pollution affects particle properties through their ability to change acidity. So let me just switch here. So my laboratory, I'm the director of the Laboratory of Atmospheric Processes and Their Impacts, LAPI at EPFL. And more or less, we study particulate matter and atmospheric processes and how they interact with each other, with a focus on their impacts on clouds, climate, and what we talk about today, health, public health and ecosystems. We are involved in field and laboratory experiments, as well as modeling, and we also do some instrument development. So we're involved with a lot of things. So hopefully you'll find some of this interesting. I'm talking about atmospheric particles, and the reason why we care about them, otherwise known as aerosols, is because they interact with pretty much every aspect about the atmospheric system. And they have multiple impacts on both ecosystems, public health, climate, even ocean chemistry. So understanding what drives their emissions, what drives their properties is really important. And one of the main aspects of understanding particles is also understanding their acidity. But here I'm focusing basically on 3 aspects that I will talk about today. Particulate matter, which you have many sources, many of anthropogenic, but also many which are natural. And how do these particles interact with health, our health when we inhale them, as well as how do these particles actually supply and affect ecosystem productivity by supplying nutrients or even inhibitors. So when we talk about particulate matter, we're really talking about emissions, stuff that becomes particles in the atmosphere, and then how the atmosphere processes these and allows them to change over time up to the point where they deposit or we inhale them. And when we talk about particle matter, there's a lot of organic species, which we won't focus too much on, but there are also a lot of things that are inorganic in nature, meaning, there are ammonium and nitrate, and there's iron and copper and things like sodium and potassium and chlorine. And so depending on which particle sources is around, you have, of course, the supply of these species. Particle size also matters a lot. Smaller particles tend to be enriched in things like sulfur and nitrogen, so they tend to be a little bit more acidic. Larger particles, meaning if you're above 1 micron in size, they tend to be more rich in alkaline substances, for example, which you find in mineral dust or sea salt. So how these components interact determine to a large degree how they affect health and nutrient deposition. Now, the key point to remember is that particles and gases are actually to a large degree in equilibrium with each other. So they're tightly coupled. And if we want to understand what particles do, you actually need to understand the whole system. And so, for example, this is just one simulation, with an air quality model that's used to predict air quality in the US.
Je fais la vaisselle après.
Can you please turn off the microphone, possible? Thanks. So what I wanted to focus on is the fact that things like how acidic particles are and how much nitrogen and ammonia have around determine actually how much mass of particles you generate. And that has profound impacts, essentially, on nutrient deposition and air quality. Now, I mentioned acidity, and this is important because acidity is a key component, which I will talk about a little bit further down. And just like to point out that particles that we breathe are extremely acidic very often. Sometimes they're not. But their acidity varies a lot, and that changes a lot about what they can do and how they can affect health and ecosystems. So if you go to places like North America, the pH or the acidity can be as acidic, for example, as your car battery or lemon juice. If you go to China, which tends to have huge amounts of ammonia around, or North Europe, then the acidity is much more like neutral, but still it could be slightly acidic. So this is a nice graph showing sort of the distribution of acidity, at least what we know so far. This is actually emerging science. It hasn't been known for a long time how acidic particles were, even though acidity is so important. But now we're getting more and more understanding. The key point I want to point out is that here, where we are, the acidity can be somewhere between 3, 4, 5 in terms of pH. That matters a lot because you can have huge shifts in particle properties and effectively their impacts in terms of nutrient supply as well as impacts on health. Another thing that we need to be aware of is that because emissions change and because climate changes the atmospheric state, also particle properties like acidity in water also change a lot over time. So this is just a time series from a recent publication showing that fog water can change its pH as well as aerosol pH, or particulate matter can change its acidity over time. Now, what does this mean in terms of particulate matter loads? Depending on how much water you have in the air and how acidic these particles are, you can actually have particles that are very sensitive to changes in ammonia, which is related to agricultural activities, or nitric acid, which has to do with emissions of NOx, which is pollution and their oxidation products, or they may not be sensitive at all. And so understanding this sort of sensitivity tells you more or less how particles should respond to emissions. And in Switzerland, we're in the center of Europe, and we also have a lot of agricultural activity going on. There's very large emissions of both things related to NOx as well as ammonia. So understanding essentially what these things are doing and how particles are responding to that is very important for understanding particulate matter loads now and in the future. And furthermore, these components contain nitrogen, which is an ecosystem nutrient. So understanding how these particles deposit over time is very important. So just to show you, depending on if you have a very acidic particle or not, you can have a lot of this nitrogen in the particle phase or not. And that determines a lot in terms of how much particles will form, as well as how it impacts things like nutrient deposition. Now, we've actually developed a theory that sort of puts how liquid water and particles and acidity of particles actually control more or less if your particles are going to be sensitive to things like ammonia or nitrogen emissions. And this is very important because this determines policy. If you want to control particle levels, you need to control some sort of emission. And that best emission policy depends effectively on what your particles are most sensitive to. And so depending on, say, for example, the aerosol or the particle acidity or the liquid water content, you can go in regions where you're very sensitive to changes in nitric acid, which is related to NOx emissions, or extremely sensitive to ammonia emissions, which is related to agricultural activities. Not knowing this state basically sets you up for policies that may not be so effective, or they may be expensive because you end up controlling everything to bring particle levels down. Sometimes you might be sensitive to both of these kinds of emissions. And if you're in that state, then no matter what you do, either nitrogen control through NOx reduction or ammonia reductions would be equally effective in controlling particle levels. Now, to give you an idea of how different places in the world change, the top map more or less illustrates the state of how places like North Europe is. This is Cabau in the Netherlands. And there, because there's so much ammonia around from cattle and agricultural activities, effectively you're saturated. You know, you have so much ammonia, basically your particles don't respond to additional ammonia. But if you actually reduce NOx emissions, then you can actually have an impact on particles. So that's what these blue dots mean. These are actual observational data put on this map. And it tells us that more or less we're always in this nitric acid sensitive region. If you go to other places like in the Southeast US, actually you have the opposite behavior. You're very sensitive to ammonia, but not so sensitive to nitric acid because the acidity in the liquid water are different. So actually understanding how what sort of domain you occupy on these kinds of maps tells you essentially what is the effective policy for reduction in particles. Now, Switzerland actually occupies both these areas depending on the season. So if you want to control particle levels or reduce, say, nitrogen deposition or control nitrogen deposition from the air, you actually need to apply policies that change depending on the season you're at. So this is actually something that's important within the climate context. Now, we mentioned nutrient deposition, and so air atmospheric particles can deliver a lot of things. They can deliver nitrogen, phosphorus, they can deliver metals like iron and copper, which affect ecosystem productivity. So we mentioned nitrogen up to now, and I'd just like to point out that, again, understanding the state of these particles, how acidic or not they are, actually controls how quickly nitrogen deposits from the air. The idea is that you have, again, NOx emissions that convert into nitric acid, and you have ammonia that's emitted from, you know, agricultural activities or cows or chicken farms, depending on where you are. And these interact and they make particles. But depending on how acidic the particles are and how sensitive they are to changes in these emissions, they actually can have these components lie around for a long time or not. And that depends if you're mostly in the particle, mostly in the gas phase in terms of these components. If you're mostly in the gas phase, these nitrogen-containing compounds deposit quickly, so local emissions redeposit very quickly in the region close to their emissions. But if you favor particle formation, they deposit a lot more slowly and they can get transported over long distances. So for example, emissions in a city may actually travel upwards in the mountains and deposit towards the top or the peaks or in the flanks of the mountainside and effectively fertilize it over time. That depends on how much water these particles have in their acidity. While if they're mostly acidic, they actually tend to deposit very locally. So understanding, again, the interaction of liquid water and acidity is important. And again, you can come up with these maps where particles deposit quickly or not, nitrogen deposits quickly or not in each of the forms that we care about. And if you have a lot of ammonia emissions and it deposits quickly and you're on this part of the diagram, for example, the blue part, then essentially all the ammonia emissions recycle locally. They get deposited quickly, they may get re-emitted, but they deposit quickly again on the ground. So this is important to know. If you have ammonia deposit slowly, then it gets emitted and it may get transported over long distances. So over time, you may be losing nutrients from the ecosystem and you need to continuously supply that. And so understanding these interactions is important. And again, if you're in North Europe, you tend to be in the domain where actually you have quick recycling of ammonia. The nitric acid tends to deposit slowly, which means that actually NOx emissions stay around for a long time. That tends to accumulate particles, so you tend to have higher levels of nitrate in the particles, but they can also get transported over long distances. If you're in other regions, you might have more acidity, and that tends to switch sort of the picture. You tend to have ammonia being transported far away from its source and nitric acid being recycled quickly. This is important again because most of the nitrogen that's deposited from the air is in the form of ammonia. So understanding if it deposits quickly or not really can determine essentially the evolution of an ecosystem over time. Now, I mentioned that acidity in the atmosphere and particulate matter emissions are changing over time. And this is a paper that's going to appear anytime soon, I guess, and any day soon in Science Advances. And this is asking the question of changing atmospheric acidity over time. How does that impact things like nutrient deposition? And I'd just like to point out here, Central Europe, this is sort of the current state of the atmosphere, where we tend to have slow deposition of nitrogen. So that means nitrogen is actually accumulating in the air and transported over long distances. But in the future, it's projected that the deposition rates will change a lot more, and effectively will go into a very quick recycling of these nutrients. And so again, understanding these changes is important because this determines more or less how ecosystems will respond to climate change. Just like to point out that it's not just about nitrogen, we also care about other nutrients. And Sam Jacquard gave a wonderful presentation a few weeks ago about how dust can impact ocean productivity through supplying things like iron, which is very important for phytoplankton. Dust can also supply other nutrients like phosphorus. And these nutrients are locked in minerals. So how available they are to the ecosystem and the organisms actually is modulated by how soluble these nutrients are. And again, acidification from pollution can really unlock a lot of these nutrients and make them a lot more bioavailable. And so just to give you an idea, these are measurements in Finokalia in Crete carried out by the postdoc in our group, Kalliopi Violaki, showing that if you have dust that gets acidified, so that means the pH drops, you have a lot more release of phosphorus in the dust particles. And so when these dust particles actually deposit into the Mediterranean, they can actually fertilize the sea by providing all these nutrients like iron and phosphorus. A very nice example was shown more than a decade ago by us and colleagues. Effectively, Asian dust being mixed with Asian pollution, and when it's acidified, it actually can create a phytoplankton bloom and enhance productivity, uptake of carbon, and the ecosystem productivity there. If there's not a lot of mixing of pollution and solubilization of things like phosphorus and iron from the acids that are deposited on the particles, then effectively when this dust deposits in the ocean, you don't see a phytoplankton bloom. It might be a small enhancement, but you can't see it from the satellites. So again, this is sort of an interaction between natural particles and anthropogenic emissions that can have profound impacts on ecosystems. This sort of fertilization can also occur in the surfaces of glaciers. And so you might have, for example, generation of algae that changes the color of the glacier and accelerates the melting of it, or snow. So, this is not just occurring over the oceans, this can occur everywhere. And we also, recently how strong the dust events can be and how it can affect air quality here in Switzerland as well. So just want to point out that these dust emissions and deposition may affect not just the blooms in the area where you see them, but actually over time, they may actually generate eutrophication in certain parts of the ocean and actually affect things like oxygen levels. And so, we did a study where over time, acidic aerosol dust from Asia gets deposited in the North Pacific. And the point is that this additional iron gets recirculated through the ocean currents and may affect oxygen levels even in the Pacific, the tropical Pacific. So what's observed as an expanded oxygen minimum zone in the tropical Pacific in the subsurface waters actually could be attributed to too much dust mixing with too much pollution, providing a lot of iron that can then cause eutrophication thousands of miles away. So this is important. Now, I spoke a lot about nutrients, but these particles that we breathe, like I mentioned, affect our health. And what's interesting is that when you breathe dust, like a few weeks ago, if you were outside in the air breathing that stuff, you know, it causes irritation. But if that dust actually mixes with pollution, a lot of the iron and a lot of the metals that are inside actually get solubilized. So when you breathe them and it deposits in your lungs, that soluble metals can be released into your bloodstream and cause all kinds of health impacts because it causes systemic oxidative stress. And so again, acidity is very important for this. And just if you take a dust particle and you look at the copper levels and you expose it to acidic conditions, remember, you know, acidity in particles is around this range. Then the copper becomes much more soluble and much more toxic. And immediately when you breathe it, it has impacts. The same thing for manganese. Iron needs a little more acidity to solubilize, but there's a lot of iron around. So if you have it around for long enough and expose it to enough acidity, it's going to cause all kinds of health impacts. And so, and it's been shown now that if you take particles, this is, say, the total amount of copper as a function of particle size. This is dust. So anything above 1 micron typically is associated with dust in our region. And then you mix it with pollution, which tends to have a lot of sulfur that are much finer. And their intersection of sizes, you generate a lot of acidity that actually attacks the dust particle. And if you measure actually how much soluble copper is around and how toxic the particles are, you can directly link it to this acidification and pollution. So the interaction between anthropogenic emissions and dust cause all kinds of health impacts. And it actually explains some things that have been around for a long time and were really not understood. Why does sulfate in the air cause toxicity in epidemiological studies when in the lab it shouldn't? I mean, there was no toxicity associated with sulfate. It's because the sulfate introduces a lot of acidity and makes the particles toxic. And so when you breathe them, they kill you basically. So just some comments. Particles affect ecosystems by providing nutrients and public health by affecting, like we said, public health through inhalation of toxic components. Acidity responses, acidity of the aerosol is very important for determining how particles respond to emissions of precursors like nitrate and ammonia, which is important because they're nutrients for ecosystems. And also the acidity levels determine how soluble and bioavailable components are in things like dust. And so the same thing that causes fertilization of ecosystems, when you breathe it, may also cause you to have adverse health impacts to populations. And so I think a lot of these questions are of direct relevance for CLIMACT, both because we're talking about urban environments where you have a lot of emissions interacting with all these precursors, but also the impacts of these emissions and their deposition to the ecosystems around will be changing a lot over time. And so this is something that we need to be aware of. And with that, I'd like to thank you.